You're good. All right, let's go ahead and get started. Good afternoon, everyone. So my name is Christopher Domas. I'm a cybersecurity researcher at a place called the Battelle Memorial Institute. It's been a pretty fun place to work. I get to do a lot of really interesting things there, but the thing I like most about it is it gives me a lot of really kind of off-the-wall ideas for crazy things to pursue in my free time. So that's what I wanted to talk to you about today, is something I've been tinkering with in my free time over the last couple months. So this whole thing has to do with reverse code engineering. So if you're not familiar with the concept of reverse engineering code, the idea is we can take an executable like a.out here, and we can disassemble it to look at the smallest instructions inside of this thing. And by looking at these individual instructions, we can figure out exactly what this program's doing. And if we can understand a program at this level, we can exploit it or modify it or copy it, probably in a way that the original author wouldn't like. So that's the idea behind reverse engineering code. So a while back, I was killing some time on this site I like called REMath. It's just a GitHub site with lots and lots of interesting articles. So I was looking for an article to spend some time reading, and this one by a guy named Stephen Dolan really caught my interest right away. So Dolan's article starts out with a really humorous observation about the x86 architecture. He observes that it is well known that the x86 instruction set is baroque, overcomplicated, and redundantly redundant. We show just how much fluff it has by demonstrating that it remains Turing complete when reduced to just one instruction. So right away, that opening paragraph just blew my mind. I thought, I've been using x86 for 20 years, and I had no idea such an instruction existed. So what instruction is this? What powerful, magical instruction is somehow Turing complete entirely by itself? So it turns out it's the simplest instruction in the entire architecture. It's the move instruction. So all move does is it unconditionally copies data from one location to another. It's really just that simple. But apparently, move is Turing complete. But what does that mean? Well, it means that any code that we write could be written as a set of moves instead, and absolutely nothing else. But the more you think about that, the more impossible it seems. When you think of all the incredible complex things our code has to do, like arithmetic and comparisons and branching and function calls and exception handling, you're telling me that we can do all of that with just moves? That seems impossible. But if move is Turing complete, then it has to be true. And the more I thought about that, the more I realized that'd be kind of hard to reverse engineer, wouldn't it, if something was written in only move instructions? Because we'd start with code like this, where even without a lot of assembly background, we can kind of look at this and understand what's going on. All we're doing here is we're loading 0 into memory. That's going to be setting a local variable to 0. Then we're pushing an argument onto the stack and printing it out with a function call. We're removing an argument from a stack and adding 1 to our local variable. We're then comparing our local variable to 100, and if it's less than or equal to 100, we jump back to the beginning and repeat this whole thing over again. So all this does is it prints something out 100 times. The idea is that the individual instructions being used, the mnemonics themselves, tell us exactly what's going on. The flow of the control flow in this program tells us what this program's doing. So it's really easy to gather those clues about what's happening here and decipher what this program's supposed to be. But if we were to rewrite this entire thing with just unconditional move instructions, we would lose all that. All the clues we had for reverse engineering are suddenly gone, and we just have this indecipherable stream of unconditional data transfers. This would be a reverse engineering nightmare. We could really stop people from understanding or modifying or exploiting our code if we wrote it this way instead. But in order to make that happen, we have to understand a little bit about what a Turing machine really is. So sort of at an academic level, a Turing machine is like this 5-tuple of things, where one of them is this finite set of states, another's a distinguished starting state, one's a finite set of symbols, you've got this distinguished blank symbol, and then you've got this transition table delta that kind of maps the cross products of Q and sigma onto the cross product of Q, sigma, in either left or right. And what that actually gives you is like this state transition diagram, a way of moving between states and changing symbols. So that's the approach Dolan took in his paper. He created this little Turing machine and showed how the move instruction could move between different states in the Turing machine. And that's a proof that move is Turing complete. So it was really fascinating to figure out that this really simple instruction is somehow Turing complete. But if you try to apply this in practice, you're going to find that that's really purely academic, because this state transition diagram is so far removed from the processors that we use every day, you really can't get much useful information about or from this proof that move is Turing complete. And Dolan acknowledges this. He sort of tongue-in-cheek concludes his article, removing all but the move instruction from future iterations of the x86 architecture would have many advantages. The instruction format would be simplified, the expensive decode unit would become much cheaper, and silicon currently used for complex functional units could be repurposed as even more cache, as long as someone else implements the compiler. So I really, really liked Dolan's idea, and I was really amused by his approach here. So I read that last sentence, and I thought, I could do that, Dolan. I'll make your compiler. Challenge accepted. So I set out to build this move compiler, but it's kind of a daunting prospect. A Turing machine is literally just a head that moves back and forth on a tape and changes symbols. How do we go from that definition to an actual compiler? Well, fortunately, Dolan's paper had a few key ideas that we could borrow from and start to build off of. So one of Dolan's really interesting ideas is that the move instruction can actually check for equality. So for example, let's say we had two numbers, x and y, and we wanted to figure out whether or not x and y were equal to each other using only the move instruction. Well, Dolan's idea was we could write 0 to memory address x, write 1 to memory address y, and then read back from memory address x, and that would tell us whether or not these two numbers were equal. So let's imagine x and y are equal. X is 3 and y is 3. This is write 0 to memory address 3, write 1 to memory address 3, and then read back from memory address 3. Well, the last thing we wrote to memory address 3 was a 1. So we read back a 1 telling us that these two values are equal. But what if they weren't equal? What if x was 2 and y was 3? This is write 0 to memory address 2, write 1 to memory address 3, and then read back from memory address 2. Well, the last thing we just wrote to memory address 2 was a 0. We read back a 0 telling us that these things aren't equal. So with 3 move instructions, we've just implemented an equality check. So that's really neat and gives us a step forward. Another key idea from Dolan's paper was there's only going to be one code path if all you've got is move instructions. You've got no way to branch. You've got no way to skip anything. All of your instructions are going to execute every time, no matter what. But if you design your program correctly, a block of moves can either have an effect or have no effect, just depending on the initial state of the system. So I'll show how we can apply that in just a little bit. Another key idea from Dolan's paper is his Turing machine required a single jump instruction to loop back to the beginning of the program. So that kind of sounds like it's cheating if you're trying to stick with just move instructions, but that really doesn't violate the Turing completeness of move, and I'll show a little bit later on how we can actually fix that issue. But this is what Dolan's program would look like. A whole bunch of unconditional move instructions followed by a jump back to the beginning of the program. His Turing machine design also required an invalid memory address for halting. We're basically executing all these moves in this infinite loop. We need some way to stop our program. So Dolan said, just assume that there's some invalid memory address, and when you access that, the system halts. So those are sort of our basic building blocks that we can try to start with. But step 2, I was a little bit lost at where to go from here. But I thought if I could kind of build on his ideas and adapt these primitive Turing machine operations for some higher level logic, if I could change his design so that it worked on actual data instead of abstract symbols, and if I added all these new operations like if-else, arithmetic logic, jumps, loops, and everything else our program needs, then maybe I could get this thing a little bit closer to something that we could actually use in practice. So the first thing I started with was how would I implement an if statement using only move instructions? Let's say we wanted to implement this simple piece of code. If x and y are equal to each other, then assign the value 100 to variable x. Of course, the catch here is we have no branches. We have only move instructions. So all our paths are going to execute no matter what. So the solution I found to that problem is to force a path to operate on dummy data if we don't want its results. So looking back at that, we've got if x and y are equal to each other, then x equals 100. So we'll first evaluate that equality using the equality via moves that we saw earlier. And if x and y are equal to each other, then we'll load up this selector so that it points to a real copy of data. Then when we say x equals 100, it's going to assign 100 into our real program state. On the other hand, if x and y are not equal to each other, we're going to load up that selector with a pointer to some scratch data. And our next block has to execute. We've got no way to jump over this x equals 100, but now when it executes, it's going to assign 100 into this dummy region of memory that's just going to be discarded. So that's how we can have different effects, even though all of our instructions are going to execute every single time. So in C, that might look something like this. We could build up an array of pointers, with the first being a pointer to the dummy data and a second being a pointer to real data. We can then use the results of our equality check to select between one of those two pointers, dereference it, and assign 100 to whatever it points to. So that's what that looks like in C. In assembly, it's a little bit something like this with NASM syntax. You've got a real copy of your variable x, a fake copy of your variable x, a real copy of y, and a fake copy of y, and then you've got these arrays to select between the two. Use the equality check that we already looked at to pick between a pointer to the real data or a pointer to the fake data. You grab that pointer out of your array, and then you assign 100 into whatever pointer you grabbed. Either that's going to assign to either real data or fake data, depending on the results of that equality check. So the solution to implementing ifs at sort of a low level is to add these selector functions, which are really just pointer arrays for all of our variables. So if you're paying really close attention, you might notice there's something a little bit funky about that equality check that we looked at. Here we're writing 0 into some arbitrary location in memory. You really can't do that. That's a pretty good way to segfault your program. But you can get around that problem as long as you limit yourself to 1 byte data. So for brevity, I'm not actually going to go over how we do that. But if you're really curious, you can look at how we can get around segfault issues in that equality check. So now that we've gotten this far, it's pretty simple to add some basic extensions to get if-elses, if-elses, inequality checks, all the things like that. But if we have to keep writing this in moves, it's going to get really, really tedious. So we can help ourselves out a little bit by building macros. So these macros are going to expand to only move instructions, but give us a way to write slightly higher level logic than we would otherwise be able to. So here's an assembly macro for checking if two numbers are equal to each other with only move instructions. Here's inequality checks. Here's a way to generate those selector functions with a macro. So we've got ifs, if-elses at this point. What we really want, though, is something a little bit more robust. We really want a way to branch and loop inside of our code. But we can do that by extending this basic if-else if idea. Basically, what we're going to do to implement branches is anytime we want to branch, if that branch is supposed to be taken, then we store the target address, we store the address of the location we're branching to, and we turn execution off. And by turning execution off, I mean we switch over all of our selector pointers to point to dummy data, so the program can continue executing, but it's going to operate on a scratch system state. On the other hand, if the branch is not taken, then we just leave execution on so that the system continues executing on a real system state. Then on every operation we're going to perform, we check if execution is on. If execution is on, we run the operation on real data. If execution is off, we check if we are the current branch target. If we are, we turn execution on and run the operation on real data. If not, we leave execution off and run it on dummy data. That's a lot to take in, but it looks something like this in practice. We've got this long stream of move instructions. At the very end, we just jump back to the beginning to execute this thing over and over and over again in an infinite loop. And let's say we wanted to implement a branch from this location to this location. Well, the way that we're going to do that is when we want to branch, we're going to store the target address that we're branching to. In this situation, we're branching to address 100C. So we're going to store that somewhere. And then we're going to turn execution off by switching all of our data pointers over to dummy data so that the future moves can execute, but they'll take effect on a fake system state. So we're turning execution off, and then on every block after that, we'll check if we're the branch target or not. If we're not the branch target, we're just going to continue executing and run on the fake system state. So we're not the branch target here, not here. We loop back around, but eventually we hit a block where we are the branch target. We see that we're at address 100C. That matches the stored target, so we're going to switch over to real data now. We're going to turn execution on, change all of our data pointers to point to the actual system state. So the future moves after this will take effect on the real system. So that's how we can simulate branching with only move instructions. Arithmetic seems a little bit more complicated at first, but it's the next hurdle we have to overcome. And it actually turns out to be really, really easy with lookup tables. And it's especially easy because we've already constrained ourselves to bite-sized data from before. So let's say I wanted to implement the increment function. It just adds 1 to a number. And I want to do that with only moves. I can do that with a simple lookup table. So in C, that looks something like this 256 elements array. So let's say I wanted to figure out what is 2 incremented by 1. I just go to element 2 in my array. This is 0, 1, 2. I see 2 incremented by 1 is 3. Simple enough. In assembly, that looks something like this to generate your table, and then the actual increment operation is as simple as going into your table and looking up a certain element in that table in order to increment that value. Decrement's pretty much the same way. Let's say I wanted to decrement the value 3. I go to element 3 in my decrement array. That's 0, 1, 2, 3. To see 3 decremented is 2. So same thing in assembly to build the table, and here's how we decrement with a move instruction in assembly. So we're getting a little bit further. We're going to need logic gates at some point, things like and or. We can do that pretty easily with lookup tables as well. Instead of and or instructions, we can do that with move instructions using lookup tables. We just generate a couple of different arrays. So let's say I wanted to find the logical and of 1 and 0. I go to my and array, I look up subarray 1, element 0, to find out the logical and of those two values is 0. The logical or of 0 or 1, I go to my or array, look up subarray 0, element 1, to find out the logical or of those two values is 1. So with simple memory lookups, I can implement logic gates as well. So this is some or macros to implement or with only move instructions, implementing and with only move instructions. Here's not with only move instructions. We still need some way to halt our program. We're executing this list of moves in an infinite loop right now. We need some way to stop executing at some point. So Dolan had an idea for this. He said, assume that there's some special invalid address that will halt your program. Well, if you've ever written anything in C, this probably sounds familiar to you. Accessing null is a pretty good way to halt your program. It's not the cleanest way. That's going to segfault your program, but it'll stop it. So that's what we're going to use. When we access null, we'll simply cease execution. So when we want to stop our program, it's as simple as trying to read from address 0. Of course, we don't want to do that every single time we hit the instruction. We want to conditionally stop our program when it's time to stop it. So here's how, using only move instructions, we can conditionally dereference null in order to segfault our program to stop it. So at this point, we've got some pretty useful building blocks for actually writing move-only programs. We've got macros for checking equality, inequality, not, and, or, ways to get data from either real memory or scratch memory, ways to increment and decrement, turn execution on and off for branching. We've got all these really useful building blocks, and if you build up enough of these, this whole thing becomes almost doable as long as you're only writing in assembly. But ideally, we don't want to write in assembly forever. We'd like to be able to compile and to only move instructions. So a C compiler is kind of a lofty goal here, but I thought let's start with something a lot simpler, a lot more manageable. So the simplest language I could possibly think of as a starting point is something that's a little bit inappropriate for a family-friendly conference like this, but it's this minimalistic, esoteric programming language that has only 8 instructions, only 2 registers, an instruction pointer and a data pointer. And for the purposes of this talk, I'm going to try to call this brain yuck, and hopefully I won't screw that up. But these are the 8 brain yuck instructions. Really simple. We've got a way to increment our data pointer, a way to decrement our data pointer, a way to increment the byte at the data pointer, a way to decrement the byte at the data pointer, a way to read in a byte, a way to print out a byte, and a way to loop forwards, and a way to loop backwards. So those are the only instructions we have available to us in BrainYuck, but we're going to add one more, a way to actually halt the system. So here's a really simple BrainYuck program to print out 1, 2, 3, 4. All of our memory in BrainYuck starts out as 0. So if we want to print out a 1, we need to get one of our data cells up to the ASCII value of 1, which is hex 31. So we're going to increment our data cell hex 30 times, increment it 1 more, and print out that value in order to print out the 1. We'll increment it again to get it up to hex 32, print it out to print out the 2, et cetera, to print out 1, 2, 3, 4. Another common paradigm in BrainYuck, to set a data cell to 0, we simply loop over that data cell over and over again, decrementing it by 1 each time until it reaches 0. So here's a BrainYuck program for printing out hello world. All they do is they do some funny looping stuff to try to get their data cells up into the ASCII range. They print out a capital H, move over a data cell, decrement it down to E, print out the E, increment it up to F, G, H, I, J, K, L, print out your 2 L's, increment it up to an O, print out the O. So that's kind of how BrainYuck works. You just increment and decrement values, printing them out as you go along. And it turns out you can do anything with BrainYuck. This is the Fibonacci number generator in BrainYuck. This is 99 bottles of beer on the wall written in BrainYuck. It's a really, really horrible programming language. This is actually way, way worse than trying to program with only moves. So why on earth would we incorporate this into our move compiler? Well, it turns out that with the building blocks we've just talked about, these brainiac operations are really, really easy to implement with only move instructions. So if I can get my code into brainiac, then I can translate it into only moves. And I happen to know going into this that there's actually already a basic to brainiac compiler out there. So I could chain the two compilers together to go from basic to brainiac to move instructions. So we've got to figure out how to write our brainiac instructions as only moves. So we're going to use some of the macros that we already created, like not is going to expand to moves, and is going to expand to moves. So all we're generally going to do is check, is this the current brainiac instruction? If it is, select real data. If it's not, select fake data, and then implement that instruction. So in this case, plus is increment the value at the current data cell. So we go to our increment lookup table to increment it and then write it back to memory, either to real memory or fake memory, depending on whether or not we're actually executing this instruction. Same thing with decrement. Moving the data pointer left is pretty simple. Moving the data pointer right is pretty simple. Halting, we just conditionally dereference the null pointer to conditionally halt the system. Input and output gets a little bit more complicated. We do the same thing as before. We check, is this the current instruction? Are we trying to output one of our brainiac values? The catch is that due to Linux limitations, we can't directly output to standard out right away. We have to ask the kernel to output something for us. So in this one case, I have to deviate from my move instructions and call an int80 in order to print out a byte. So I'm asking the kernel to print out this byte for me at this point. So I'll show how we can fix this later and get around the int80, but that's the easiest way for us to get started. Same thing for reading data in. We're going to need an int80 in order to ask the kernel to read in a value for us. Looping gets a little bit more complicated, but it's the same basic premise. Use your move instructions to check whether or not you're currently on this brainiac instruction. If you are, switch over to real data. If you're not, switch over to fake data. And set up your branching targets, since this is one of our branching instructions. Same thing for branching in the other direction. So with that, we've got all of our brainiac instructions implemented as just a series of move instructions. So that entire tool to do that translation for us is what I call the MoVfuscator. So I wanted to demo that really quickly. So the tool itself is really pretty straightforward. It's just a couple hundred lines of code. So if we open up our compiler here, we'll see all it's really doing is it's reading in a brainiac instruction, and then it's printing out the move instructions that would correspond to that brainiac instruction. So, for example, here, if the brainiac instruction is increment, here are the move instructions in order to implement that. So really pretty simple. But what that allows us to do now is it lets us take a brainiac program, like this is a ROT13 cipher written in brainiac. We can now feed that brainiac program into our compiler and output corresponding assembly for that. We'll then use NASM to assemble our program, use LD to link our program. We can use opstump now to actually check the results. Let me try that again. So now we've got a program written in only move instructions that will hopefully implement a ROT13 cipher for us. So if we go ahead and run this, I should be able to say something like hello DerbyCon, and using only move instructions, it'll run the ROT13 on that. So I think that's kind of neat. We're using move instructions to do actually fairly complicated things just through a simple set of unconditional data transfers. But there was something that really, really bothered me about this. We've got two non-move instructions in this loop. If we look back here, you'll see that it concludes with a jump instruction, and occasionally in here we've got an int80 instruction to do I/O for us. So that doesn't violate the Turing completeness concept, but it still really bothered me that I had non-moves inside of this program. But it turns out that we can actually fix these things if we just set up our execution environment correctly. So getting rid of the int80 turns out to be actually pretty easy. We can do that with memory mapped I/O. So by mapping the standard in and standard output streams into our process's memory, we can then access standard in and standard out just through move instructions. So we can use move for I/O after we map those streams into our memory. So int80 is an easy one to get rid of. That jump at the end, that one's a little bit more complex. So there's a lot of ideas I had for getting rid of that final jump. The easiest way I found in the end was to set up our program to be its own illegal signal exception handler. So what that'll let us do is tell Linux we want our program to handle its own exceptions. We'll set the SA no defer flag. That'll let us trigger this exception multiple times. And then we're going to replace that final jump instruction with an illegal move instruction instead. So when you think about illegal move, you might be thinking of something like a null pointer dereference, but that's actually an illegal memory access, not an illegal move. In fact, the only illegal move instruction I could think of in all of x86 is trying to load the CS register with a move instruction. You're not supposed to be able to do this. You can encode that instruction, but that'll throw an illegal instruction exception. So when that exception gets thrown, the program will try to handle its own exception, and it will loop back to the beginning of the program without having to use a jump. But that's going to cause recursive exception handling to prevent a stack overflow. The last key to the puzzle is to reload the stack pointer on every iteration of our program. But with that set of steps, we successfully get rid of that final jump instruction so that we can have a purely move program. But if we've got to stick to BrainYuck for all of this, this thing's going to be entirely unusable because it's way harder to write in BrainYuck than it is to write in moves. So that's where this other compiler comes into play. So I did not write this other compiler. Fortunately, somebody else went through the grunt work of creating this thing. But there's a compiler out there called BFBasic. What BFBasic will allow you to do is take a basic program. Like I wrote this 99 bottles of beer on the wall program in BASIC. Should be pretty easy to decipher. We set the number of bottles of beer on the wall. Then in a loop, we print out the first set of lyrics, the second set of lyrics, the first set of lyrics, take one down, pass it around, decrement our bottles of beer, print out the lyrics, and we can continue until we have no more bottles of beer on the wall. As far as the lyrics go, the first set of lyrics varies based on whether or not you have bottles of beer left, as does the second set of lyrics. So pretty simple program, but the BFBasic compiler will allow us to translate that into BrainYuck. So now we can open our BrainYuck version of this, and BFBasic has conveniently translated that into, down here, 15,000 BrainYuck instructions. So if we now take that and we bring it into our MoVfuscator, we'll compile that program into only move instructions. We can verify that we do in fact have nothing but a tremendous stream of moves, and I don't know how fast my computer's running today, but I think it'll finish obj dumping this before the end of the presentation. We'll give it. You can imagine there's a little bit of bloat in program size. I think it went from maybe 100 bytes to about 8 megabytes. But you will see we got rid of that final jump at the end with just this illegal move instruction. When it hits that, it'll begin executing our program back from the beginning. So now if we go ahead and actually run this thing, you'll see nothing happens because it is really, really slow. But if you give it enough time, it'll actually start printing something out for us. It'll print out 99 bottles of beer on the wall. And maybe if we give it even more time, it'll tell us how many are left when we take one down. It's 98. So it seems impossibly slow, but you got to remember it's not just printing out the lyrics. It's actually doing arithmetic and comparisons and function calls and all these really advanced things with nothing but this giant stream of infinite move instructions. So it's actually really cool that you can do that. So we're just going to let that execute, and maybe it'll finish at some point. But this means we can do anything now. If we can compile it with BFBasic, then we can translate it through the MoVfuscator into only move instructions. So I started trying to think of interesting things that we could make. So here's a program written in only moves that can factor numbers for us. So if we go ahead and run this, it'll actually factor things for us. I mean, that's fairly advanced math occurring with nothing but a bunch of unconditional move instructions. And of course, it doesn't clean up easily. The way our programs stop is by segfaulting themselves. What else? So we've got a program written in only move instructions that can actually generate prime numbers for us. So again, sophisticated math with nothing but moves. In fact, here's a complete CSS decryption cipher. written in only move instructions. Here's a role-playing game called Lost, written in only move instructions. I even MoVfuscated the MoVfuscator, so I have a program written in only move instructions that compiles other programs into only move instructions. Unfortunately, it takes days to complete, so. But I was really excited with how this was going. It was a lot of fun to watch nothing but move instructions do real computation. But I went back to my original question, sort of, is this an effective anti-reverse engineering thing? How would an experienced reverse engineer actually approach this problem? And I kind of thought, well, I'm an experienced reverse engineer. What would I do if I opened up a file and I saw nothing but hundreds of thousands of move instructions? Really, I'd find something else to reverse engineer. I reverse engineer because I think it's fun, and this doesn't look like fun at all to me, so it'd be pretty effective just on those merits. But more seriously, thinking about this as an anti-reverse engineering technique brings up some interesting observations. So going back to the 99 bottles of beer on the wall demo, if we had written that in C, the first function would look something like this in the control flow graph. The first lyrics would look like this. Second set of lyrics is more simple. If we wrote all this as one big function, our control flow graph would look something like this. Now, an experienced reverse engineer could look at this and in a couple seconds tell you exactly what was going on here just by looking at the control flow graph. So other obfuscation tools usually take your program and they try to add a lot of complexity to it to make it more difficult to reverse engineer. So you might take this same program, put it through a different obfuscation tool, and it will become really, really complicated. On the other hand, if you put this through the MoVfuscator, this is what you get out. It's a line, because there are no branches. There's no control flow going on here. So this is 99 bottles of beer on the wall. This was the Rot 13 cipher we saw earlier. This is Towers of Hanoi. This is a Mandelbrot fractal, and this is that Lost role-playing game. So you might notice a pattern here. Pretty much everything comes out looking exactly the same. And these are fun to look at in IDA, sort of the de facto reverse engineering tool. IDA really doesn't like it when you've got one block of 100,000 move instructions. It will crash every single time you try to look at anything. So it's effective in that regards too. And I just thought it was really interesting that it's the opposite of other obfuscation tools. It simplifies programs in order to obfuscate them. Every program becomes exactly the same thing, and there's no dead code. A lot of obfuscation tools add junk code for you to sift through, but there is no dead code here. There's only code that sometimes works on fake data and sometimes works on real data. But more realistically, if you really were determined to reverse engineer this thing, what a reverse engineer would do is that they'd see that there are these patterns in the move instructions. Groups of move instructions are implementing simple basic operations. So they would reverse engineer their moves back to the basic operations and then reverse engineer the basic operations. But that's actually really, really easy to thwart. So I added some routines that'll actually shuffle the individual move instructions inside of these blocks, so you don't end up with any patterns of moves inside of your code. You can even insert junk move instructions inside of these blocks so that no two blocks ever look alike. It's easy to interleave your blocks so that you can't separate them into more fundamental operations. And then you can even rearrange the basic blocks in a lot of situations because they often operate independently of one another. So it becomes kind of a reverse engineering nightmare when you can repermute the entire program every time you compile it. And it's especially effective in the move world because all the instructions look the same already. So you'll compile something one time and it'll look like this, compile the exact same thing and it'll look like this, and compile it again and it'll look like this. It's just a nightmare to sift through. And even without this, what I was finding when I was writing this is I occasionally made a mistake. I introduced some kind of bug and I had to dive into GDB and reverse engineer the move instructions to figure out what was going on. And even though I had just written those instructions myself 5 seconds earlier, I could not keep track of what was happening because everything looks exactly like everything else in the program. So it's pretty daunting, but there are some pretty obvious limitations here, namely the speed. It's not fast. And one of the biggest reasons for that is the way that jumps work in our MoVfuscated code. When we want to jump from one location to another, we switch back and forth between real data and dummy data. So if you imagine jumping forwards isn't too bad. If I want to jump from here to here, I simply turn off execution here, I execute all these moves operating on dummy data, and then I turn on execution here. So you've got a small number of wasted moves in between those branch locations, but jumping forwards, not backwards, or not a problem. Jumping backwards is where the real problem arises. If I want to jump back from here to here, I turn off execution, my entire program has to execute again before it can turn on execution here. And that's especially problematic because of the way BrainYuck sets values to 0. It does a small loop decrementing a value over and over again until it reaches 0. So every time I want to decrement a value by 1 in BrainYuck, my entire program has to re-execute itself on dummy data. That's going to make things really, really slow. To highlight that, we can check on how our bottles of beer program's doing, and it's not even close, but it's getting there. So it seemed unusable, but I kind of figured, well, I've gone this far and I've had a lot of fun with it. Would a C compiler really be that much more complicated? Turns out the answer is yes. What I had so far was maybe 200 lines of really easy code that took about 3 hours to write. Getting to a C compiler was thousands and thousands of lines of really, really complex code. But it actually turned out to be fairly straightforward. So I started trying to implement an arithmetic logic unit. And if we want to be able to compile C, we need to go from bite-sized data that BrainYuck was using into full 32-bit arithmetic. The problem with 32-bit arithmetic is you can't just use lookup tables for it anymore. You don't have enough memory for these giant 32-bit lookup tables. So you've got to do it a little bit more advanced, but it's still doable. So here's some assembly macros that will expand to only move instructions for implementing 32-bit adds. All we do is we cascade a bunch of 8-bit adds, and when we expand those macros, a 32-bit add with only move instructions looks something like this. So it's really not too bad. 32-bit subtraction is similar. It expands to something like this. Shifting gets a little bit more complicated. These are macros for left shifts, which expand to this. Right shifts expand to this. Multiplication is where things start to get bad. So here are multiplication macros that will expand to only move instructions. So that's 32-bit multiplication using nothing but unconditional data transfers. But division's where it gets really, really ugly. So here are 32-bit division macros, which expand to a little over 7,000 move instructions, which is kind of ridiculous when you think that one div instruction would do exactly the same thing. But the point is it can be done. We can use moves to accomplish all of these things. So I kind of took that as a starting point and really ran with it to build this compiler. So I used a compiler called LCC as the front end for this thing, and I wrote a move backend for this. It's a little bit of a challenge because you need to preserve so many registers for yourself just for shuffling around memory that you can't really give much to the compiler front end. But I allowed LCC to keep ESI and EDI to itself, use all the other x86 registers for memory shuffling. Had to define a new calling convention for move instructions, create an emulated stack with move, integrated that 32-bit arithmetic logic unit, simplified the way that our branching worked through those dummy selectors, had to painstakingly implement all 102 intermediate language instructions with only moves for the LCC compiler, but it turned out to go a lot smoother than I had anticipated. So that's what I call MoVfuscator 2, this complete C compiler that will compile C source code into only move instructions. So I was trying to think about what the best thing to create with, or to demo with MoVfuscator 2 was. When I was a kid, I always really liked the game Nibbles or Snake or Worm. So I coded up this little Nibbles game in C. It's really only a couple hundred lines of code, but we can now run that through our MoVfuscator, the MoveCC compiler. It'll MoVfuscate that for us and translate it into just a tremendous number of move instructions. But now we can run this program and actually play Nibbles with only move instructions. And you know what? It's actually kind of fast. This is almost usable at this point. So I thought it was really cool that I could actually run real C code using only move instructions. But my compiler was lacking for a little while because I didn't know how to implement floating point math with only move instructions, because in x86, move cannot access the floating point registers. So the solution I came up with for this was to create a move-only IEEE floating point emulator. It turns out to be about 500,000 move instructions to emulate floating point math with only moves. But what that lets you do is really any floating point stuff that you wanted. I thought the best way to demonstrate floating point math would be to write a 3D graphics engine. So I wrote this little graphics thing in C. So we can compile that with our MoVfuscator, linking in our move-only floating point libraries now. And it's, let's see, so if we dump that, we could sit here all day and this won't finish because that's a lot of move instructions. But if we go ahead and run it, we'll see we've actually done matrix manipulations, cosines, sines, all sorts of crazy transforms that implements. So it's a lot of work for a spinning cube, but it's the best way to demonstrate, I think, floating point math with move instructions. So I was pretty excited about how that turned out. And really, this is a complete C compiler. So I've got examples for calculating E, pi, square roots, AES, DES, MD5, SHA-256, Bitcoin stuff, games, fractals. I even downloaded a public ray tracing engine so that I could generate ray traced images using only move instructions. And it's fun to just watch it churn away. And I think, as far as I know, this is the world's first single instruction C compiler, probably because I don't think anybody's ever wanted such a thing before. But it was a lot of fun to work on, and it got me to thinking, what other Turing complete instructions exist? We know move is Turing complete, so what else is like that out there? Well, I thought it seems obvious then that XOR must be Turing complete if move is Turing complete. Because if you think about something simple, let's say we wanted to move the value 1, 2, 3, 4 into the EAX register, we could do that with just a pair of XORs instead. We could XOR EAX with itself to clear it out, and then we could XOR EAX with 1, 2, 3, 4 to get EAX set to 1, 2, 3, 4. So with just a pair of XORs, we can simulate a move. So I turned that into the MoVfuscator, which will compile C programs into only XOR instructions. So really all this thing ends up being is a little Python script that takes the output of the MoVfuscator and translates those move instructions into an equivalent set of XOR instructions. So let me try to get this right. So what we do is we compile our program with the MoVfuscator, and then we run it through this XOR translator in order to get this XOR-only program. So this particular one we're using to print out prime numbers. So now with only XOR operations, it just calculated all the prime numbers up to 10,000. So I thought, what else is like that? What other things like XOR are out there? And I found all sorts of instructions we could do the same thing with. So there's XOR, a pair of AND/ORs will do the same thing. So I made the AND/OR-fuscator. If you're creative with the way you use subtraction, you can combine a bunch of sub-operations in order to implement a move. So that's the sub-fuscator. My favorite's the comp exchange fuscator. I couldn't quite get comp exchange to be Turing complete by itself, but if you combine it with another exchange instruction, you can make that happen. So you can write, or you can compile your C code into only comp exchange instructions. Or another good one, I was running out of names at this point, the R-fuscator will compile your C code into only single bit shift instructions. So this one gets to be actually slower than the brain yuck code ever was. So I won't actually run it, but we can actually see it compile, and then we'll at least obj dump it when it finishes compiling that. So now we've got a complete program with nothing but single bit shifts that'll actually do really anything that we could do in C. So I was still having fun with this, wasn't ready to call it quits, trying to think of ideas for MoVfuscator 3.0. And a friend of mine pointed me to this paper showing that the x86 memory management unit is Turing complete. What that means is that you don't need any instructions in x86 for Turing completeness. The page faults and exception handling mechanisms in x86 are Turing complete by themselves. So that research is courtesy of two guys, Julian Bangert and Sergey Bradas. Pretty sharp guys, but I think my goal for next year would be to have a C compiler that outputs no instructions. But wrapping everything up, I really don't know if this is a legitimate anti-RE solution. I just thought it was an incredibly fun little side project to work on for a little while. So if you're interested in this at all the sources on GitHub, you can get the original MoVfuscator there. That's the brain yuck version. You can get the C compiler version. You can get all the other blank fuscators. There's even a crack me there. If you like to reverse engineer and want to try your hand at move-only reverse engineering, you can check out that crack me. I've got some other stuff up on the GitHub. At DEF CON, I showed a tool called Recyc, which lets you restructure the control flow of your programs in order to draw images. Serves absolutely no purpose, but it's also kind of neat. If you like things that serve a purpose instead, there's also some code up there for an architectural privilege escalation vulnerability built into the x86 architecture, so you can check that out too. And I'll be tossing some other random things up there in the future. If you have any feedback or ideas on this, I'd love to discuss it more with you. It wouldn't be where it is today without people's input. And if you want to track these projects, you can follow me on Twitter. That's XOR, or if you want to have a discussion more than 140 characters, feel free to email me. I want to see if our original, well, this thing hasn't even finished option dumping yet, but I want to see if our original bottles of beer on the wall program is finished, and it's not close. But I've got a few minutes left if there are any questions. We'll let this thing keep churning away and see how it does. Yeah. Yep, so all the different obfuscation techniques are pretty independent of one another. So if move obfuscation was not enough, you could certainly interchange them or combine them in creative ways to complicate things even more. Mm-hmm. Yeah, so the question is, with the mmap technique to get rid of the int 80, don't you need additional non-move instructions? You do, but the difference is that they can be in the loader itself. So it could be completely separate from your program. That could be part of the OS, so that your program could be only moves. Okay, so our Brainiac program actually finished, and I think I'm out of time, but I really appreciate everyone stopping by to check this out, and I'd love to get feedback or ideas from everyone. Thanks.